morning. It's an honor, a pleasure to be here and exchange some slides and ideas about the topic of digitization and Internet of Robotic Things, and to check out some of the current possibilities in site-specific crop management. I'm hoping that today the take-home answer we can have is to address what enables robotics to succeed in future farming. Yes, my name is Redmond Shamshiri, so I'm an associate professor of robotics and land technique in New Brandenburg University of Applied Science in Germany, and I'm also affiliated with Leibniz Institute for Agrotechnik and Bioeconomy in Potsdam. Yeah, I will go through these outline how agriculture is changing, the use of digital technology in agriculture, what we have been doing in the last 40-45 years, agricultural robotics, and a relatively new concept called Internet of Robotic Things, where we connect the robots with connectivity. And then let's see what to expect in the next 10 to 20 years with the emergence of Agricultural 5, and then we will have some summary and conclusion. Okay. All right, so until the 1850s, 1900s, we have been using animals and human power source in the field. Everything was manual. And then after the Industrial Revolution, we had a lot of machineries, tractors in the fields until 1980s. And with the emergence of GPS, computers, data processing softwares, and sensors, and soil mapping, soil sampling, and this kind of technology, we started practicing something called precision agriculture. And then the thing is that the data in precision agriculture was always offline, so we had to collect data and process it later. But starting in 2010, with the widespread of internet, Wi-Fi, mobile apps, IoT gadgets, AI technology, all these drones, robots, we have started practicing something called digital agriculture, and that's completely changing the way we are looking at agriculture. So it's a transformation of agriculture, what is called Agricultural 4. And nevertheless, what we have been doing the last 200 years, try to increase the yields and having higher profits. And a classical response to this yield increase was that, okay, with bigger machinery during the Industrial Revolution, we believe that bigger machineries would contribute to higher yields, and then we can feed more people. Yes, that was partially right, but it was not sustainable because we used inputs evenly, which led to inefficiencies. But in the last 40-45 years, we are trying to address inputs in a site-specific crop management way. And we believe that now machines should be smarter, smaller, and connected. Not necessarily the bigger machine would contribute to higher yield. So with that, then we are expecting to have more efficient resource use, and then we can increase yield in a sustainable manner, not just increasing and destroying the environment. And as you see in this field, we have part of the field has different variabilities. It could be soil moisture, it could be nutrition, it could be weeds. So we can now treat the fields in a site-specific way. In Germany, we call it teilflächenspezifische Bestandesführung. And now what is that? That is site-specific crop management. Let's first have a definition to agree on. It's collecting and processing data for adapting inputs to spatial and temporal variability for maximizing outputs. Hence, we are reducing waste and increasing yields. If you look at this modern farm, you can see that we have different kind of sensors in the field, and now these sensors could be proximal sensors, in situ sensors, remote sensing, drones. Even sometimes you use mathematical models as a sensor. So at the end of the day, we are collecting some data, and now these data needs to be connected to some platforms, data processing softwares, cloud-based, computer-based, and to machinery, and then to have some actions in the field, make some decisions, and have some actions in the field. Yes, and then we are trying to optimize inputs for outputs. And then what are these inputs for agriculture? Inputs are water, climate, pesticides, fertilizer, soil, seeds, labor, capital. And in modern agriculture, yes, we have energy, machinery, robots, and automation. We have to optimize these to produce outputs, and the outputs are yields. crops, livestock, honey, fish. And the question is that how to minimize these inputs for higher outputs, and the answer is to use digital technology. So, looking at these farms, a little futuristic farms that this animation we created in our startup, we have different kind of sensors in the field, wireless weather stations, data loggers, sensors in the soil, sensors on the air, sensors on the machinery. These sensors could be powered by solar panels or could be battery powered. And now they are also interconnected. They're connected with different farms. And in the fields, we also have different kind of machineries, robots that you can see. And with all that, we can summarize it as sensing, connectivity, data processing, robots, machinery, and power source. And now let's focus on the robotic part. The major technology for this transformation of agriculture, I'm sure you're familiar with variable rate technology, VRT, ground robotics, machinery, aerial robotics like drones, IoT and wireless sensors, plant phenotyping approaches and methods, and artificial intelligence. For sure, we cannot keep talking about everything, but the focus of this presentation is on ground robots and the connectivity. So what we have been observing, especially in the last 10 to 15 years, one of the key enablers for this transformation are the rise of agri-tech startups and robotic startups, that you can see that they are coming with innovative, specialized solutions that are entering the market, and the trend is toward developing modular and scalable solutions. The robots that they use electrical energy, not diesel. They can be used for rural connectivity, for infrastructures, for knowledge transfer, for field adaptations, and for data ecosystems and platforms. Some of the examples could be this exotic, customizable robotic platform that when farmers buy it, they can adjust its size based on their field. This is a major issue for farmers, that when they buy a robot, now they can use it only for specific fields. Now this startup came up with this innovative solution that you can change the robot size dimensions. Another startup came up with this solar charging station for electrical tractors. The other problem, especially in European countries, in Germany, is that when farmers want to buy electrical tractors, they do not have infrastructures to charge that. Another one is the world's first fully electric combine harvesters. That one startup called Lintos came up, it's Australian startup. And now another innovative solution is that we do not need to always keep developing robots for fields, but we can change our fields to work, to cope with the robots. Dr. Manuela Zude at ATW in Potsdam, she's my colleague, and she's changing the design of that orchards so it could be used for digital agriculture. That's also one approach. Now, why would we even need this Internet of Robotic Things? What are the challenges and limitations? The problem is that no matter how you have a good engineering team, it is always challenging to come up with a solution that gives you a fully autonomous robot to work in different kind of plantations, fields, orchards. It's very challenging. So for example, in oil palm plantation in Malaysia, you would need constant and live inspections because of, let's say, Ganoderma basal disease. You want to have early disease detection, prediction. Before it happens, you want to know it. So you need to have constant data monitoring. You cannot have sensors in one place. It would be too expensive. You need robot agents to move in the plantations and start monitoring. Then your robot needs to have some sort of connectivity because you need live data. And in plantations, you don't have internet. They are in remote areas. Robotic harvesting is another field. The image recognition, it could be very challenging. It has a lot of limitations. That's actually the most challenging part for robotic harvesting, that is stopping it from being commercializations because of the leaf occlusions, because of the variability in the light conditions, overlapping of the fruits with the leaves. And the solution again is to have human in the loop. So human could decide and detect the fruits, pinpoint it on a simulation platforms, and let the robot go pick that fruit. We'll show it in a couple of slides. Another one is even if you have a fully autonomous system, a lot of countries, they have policies and legals and safety regulations. You cannot just let the robot be in the field on its own. You need human supervision. That's why this, for example, robot supervision, in order not only supervision but also to control. Sometimes your robot is stuck in a remote place and you cannot keep going to the field to get it out of that singularities or out of that dead zone. Because of this, we need connectivity. Can we go to the next slide or? Oh, yeah. Okay, look at some of the practical examples. This is a company called EarthSense by Professor Grisha of University of Illinois Urbana-Champaign. He's deploying this kind of big, expensive robot in the field, in oil palm fields. As you can see, it is going autonomous, and needless to say that autonomous navigation is already very challenging, but it is also doing some human control, and you can see that humans are around it because you have ditches, you have holes in the fields, you don't want to destroy that robot, you don't want to destroy the palms. Some farmers, they use drones for spraying, for even cutting. There is a company in Malaysia, I know, Cambian Network, they try to come up with this solution to cut the fruits by using drones. It's very challenging and you have to do manual control. Another one that I was involved with, this red tractors, electrical hoof track. Actually, we designed a follow me solution for that. The idea is that the farmer, he can walk and the tractor follows him, but still you need some supervision, you need some safety regulations. And the other one is in the simulation environment with Opal RT technology simulation that we collaborated. Now, because of all this, okay, so now we need connectivity for the robots. The topic or the term is called Internet of Robotic Things. This is a valid term. A lot of publications talks about it. In order to have that, you need two main ingredients: a simulated robot and an actual robot. Whatever you have in a simulation is like a digital twin, by the way. So whatever you have in a simulation, you need to also have on the actual robot. In this study, we focus on the application of IoRT, Internet of Robotic Things, for human supervision and control. And we designed path generation and tracking for the simulated robot, collision avoidance with fuzzy logic algorithm, and we deployed long-range wireless connectivity. The very same thing also on the actual robot. This is the platform that we purchased, and we turned it, this was just a manually controlled platform. It has a diesel engine, but we changed it after like 1 year of work. We changed it to a robot. Now it could go autonomously by doing waypoint GPS waypoint following. And yes, it has this kind of dimensions. It's a 4-wheel Ackerman steering tractors, maximum steering angle of 25 and maximum speed of 10 kilometers per hour. And then the sensors that we customized and designed on this one. These are a little bit of technical. I'm not going through the detail, but for those who are interested, so for autonomous navigation, you need to have a steering control and a speed control. And this is one of the most common used method is called GPS waypoint following via pure pursuit control algorithm and PID control. And this is something that you see, we designed it, deployed on the simulated robot, we tested, it worked. You can see that it's following the path, but that path is a combination of waypoints. And after it was successful, we deployed it on the real robot. And this is the architectures to connect the simulated robot and the real robot. For the communication, we used LoRa, long-range wireless connectivity. Point-to-point, it can go to up to 2 kilometers. Depends on the obstacles in between. If you have a good line of sight, it can go even more than that. With some new LoRa modules, it can even go to up to 10 kilometers. But we had repeaters in between, so we could extend it. So we designed our own local network. And why? Because you don't have Wi-Fi, you don't have internet, you don't have infrastructures in remote area. You cannot depend on internet. You need to have your own local network and also to be secure. And these are some of the sensors that we custom designed from scratch because we also wanted to experiment with the sensors. For example, you see that 6-channel infrared, that's a very innovative solutions, and now after that some companies are also coming. The idea was to give farmers something that is low cost yet efficient, and they can change it and is robust enough to withstand in the field. the LiDARs that you buy, usually they are not IP67 proof, or they're not waterproof. So, but anyway, we had also one-dimensional LiDAR that goes to up to 12 meters. It can detect obstacles. And that PCB that you see, we designed it, manufactured in our own startup for this specific applications. And the communication between the sensors and the robot ECU is via Canvas and its industrial protocol. So if there's any technical questions, I can answer that later. And this is the overall architecture of the robot controller. So the robot has a computer for the collision avoidance and waypoint tracking, and then it has its own computer, like the ones that you have, everyone has nowadays on their car. It's called the ECU of the system. As an industrial controller here, we had high-duct TTC that is responsible for controlling the actuators. Yeah. So then we have feedback from our sensors going to the computer. That's a ROS computer, data processing, collision detected, left, right, forward, what happens, giving to the high-duct TTC and controlling the robot. I think this one needs a new battery, huh? Okay. So now, as mentioned, everything we need to have simulation and reality. So the algorithm was first tested. This is a fuzzy logic collision avoidance algorithm, was tested in the simulation environment. The good thing is that you can test and tune your algorithms in simulation without going to the field. It gives you up to 90-95% accuracy, the same thing that you can expect in reality. And yes, it really accelerates your development, your prototyping. And this is in our experimental field. We set the robot program so it can keep distance, let's say 35 centimeters from obstacles to the left or right. And if you see something in front, then it stops. So this very preliminary phase, it worked. We have a simulated system, a physical system, both of them works. And now test it. Okay. So there is one important question that maybe those who are familiar with robotics will ask, that okay, with this LoRa, the bandwidth, you cannot transmit so many data, raw data. So how we did that? For example, LiDAR, it generates a lot of data. We don't need to transmit all that raw data to the receiver. We wrote some Python codes to filter that one, and then out of that, we have a summary of the message. For example, if it's seeing obstacles in that specific angle, in that distance, this is what we are interested. And then even we can use it as a threshold that anything in the range of 15 angle below 15 degree, for example, or range of 2.5 meters, that is obstacle. And now please stop the robot. This is something that we transmit. We don't transmit all the raw data. To make it an example, it's like you have a cell phone, you take a picture, the picture has like maybe 3-4 megabytes size, you don't send that. If there is a face, a human in the picture, 1, 0 or 1. There is a human, 1. You send that 1, and that's as easy to send with LoRa. Okay, and now we talk about simulation and reality. Another question is that these two environments, simulation, you use X, Y. In reality, you use latitude, longitude. How we translate these two? Using these equations, we translate in real time. Simulation translate its X, Y. Both of the, by the way, maps should be identical. Otherwise, you don't get a good result. And simulation translates X, Y to latitude, longitude, and the other way. And these are some of the hardwares that we used for this teleoperation. The sensor nodes, the PCB that we have been using even for our weather station, wireless weather station, the very same thing, but with some change in the software and some hardware adjustment. We change it, we use it for transmitting data. Here I am just showing the very first result. That thing in my hand, it is the distance, because of the video we want to show in one picture, but the distance could be up to 2-3 kilometers. It's long range. And the other one is the simulation environment, that the simulated robot on a jack, you can see that it goes left and right, it's controlling the real robot. And the other one is shows the robot that doing target following in real time and transmitting data. And here, so this is doing waypoint following, targeting that small cube is a target, and the messages, you can see the LoRa messages are being generated and being transmitted to the real robot, and on the other side is the interfacing of the way we have interfaced the real robot and the simulated robot, and now the real robot is doing navigation and collision avoidance inside the orchard. This is the berry orchard in Germany. You can see that it's about to hit the left or right, but because of the sensors that it has, it avoids it. And now this is also the simulation. Okay, and now this is the final demo. The idea is that the farmer is sitting in his farmhouse. From 2 kilometers away, he can see the robot, he can control the robot. Right now, he's creating a safe path. He's telling the robot where to go. With his mouse, you can see that's just his mouse. He says, follow me. And the simulated robot is following and generating a path. This path is called a collision-free path, safe path, something that farmers has generated that. And this is the path that we transmitted with LoRa. This is the way we are transmitting, upload it to the real robot. The real robot is in the field. It already has its own commercial GPS-based navigation system. Receive the path, follow the path, and now generate a response. This is the response from the real robot. And of course, this is a very long process. I mean, farmers wouldn't draw this kind of long path, but we did it for the sake of demonstration. The idea is that if your robot is stuck in a corner, you want to bring it out. So just maybe a short path, not this long path. And we did all that because it was actually part of a main project, a 4-year project, a funded project called Sunbot. It was about developing these autonomous electrical tractors for autonomous mowing, cutting the grass. So everything, again, we had to do the simulation, safety, collision avoidance, human detections, designing sensors. And yes, it was also supposed, it's electrical tractors, even the mower is electrical. And now let's see if we can, I mean, this is our final demo for the final project. The sensors that I showed earlier, after testing on that small robot, we deployed on this real robot. Actually, it was not a robot, we purchased it. This is a human-driven platform, hoof track. We turn it into a robot. So now it's going autonomously, and you can see, even in a slow motion, when it sees bushes on the left and right, how accurately, beautifully it responds to that and avoids hitting the bushes. Here is doing GPS-based navigation. If it sees something, the collision avoidance system must stop it and report it to the cloud and to the farmer, to the supervisor. Right now it's going, and this one of the students is in front of it. So the robot gives you some alarm, sound alarm, and then you can also see it on the web interface. And these are some of the closer view of the sensors that we designed. The sensors are prototype, but they are waterproof. They are industrial communication protocol CAN bus. This is exactly what you're also using in your automobiles and cars. And those 2 toolboxes, GPS-based navigation and collision avoidance toolbox. And all the data, transmission of all the data with the sensors and ECUs are within that pair of wire that is called CAN bus. So that's. And then this is this. Now this is the web interface. So maybe you will ask, okay, now what kind of softwares the farmer is going to use, because not all farmers know how to play with the simulation software. So they can use web-based software that we have developed for them. Right now you can see that this is an autonomous system going for autonomous mowing. The algorithm, it sees some obstacles, it finds its way and try to avoid it. And that is a simulated sensors. This is interfaced with a real robot. I did not bring the real robot here, but we have demos that this moves, the real robot moves. The real robot moves, this moves. So it gets updated. One of our clients wanted this solution for barn, for mobile sensing. He has for livestock. He said, I want to give a path. The robot must follow that path. And when I say sense, it stops, do the measurement, for example, CO2, NH3, microclimate, whatever. And then it stops, sense, send the data to a dashboard I can see. So he do not want to purchase like hundreds of sensors and keep placing them, but he want to have one sensor installed on a mobile platform. This is relatively an innovative idea, and he asked me not to share it everywhere, but you can see that he can, the robot can follow his mouse, and when he sends sense from the website, from his home, he could be in another country, by the way. the robot can sense and send the data. So he can see temporal and spatial variations in environment. Another application is this robotic arm. Here I'm controlling the simulation from this just prototype joystick that we made. You can see how fast, how real time, because it's a question of how real time the system could be. This is how real time it can be. And now even we can send a path, and the question is that how accurate it can follow that path. If yep, sorry. So can you place a space, please? Space bar. Not the other on the other slides. You have to, I need to show this video if you have access. The other one, I mean, this one. Click on this. No, this. Yeah. So this is using now pick and place, and sometimes when the situation is complicated, a human can intervene and control the robot from remote distance. Never mind this, the other one is not showing. And now for the robotic harvesting, I mentioned that could be quite challenging. Here, this was a consultancy project, and later on, another company came up with a commercial solution that you can see. We proposed using linear actuators because it's easier to detect the fruits, 0 or 1. Make the image binary, and those robotic harvesting systems in the market that are commercial, you can see that they are benefiting from linear actuators. Okay, now what to expect in the next 10 to 20 years? This agricultural 5 is about to happen. We will see more digital twin solutions, swarm robotic principles, development of small scale robots, that each of them are focused on a local task but contributes to a global, for example, like pollinations, scouting, moving robots. And then connectivity with IoRT and 5G and virtual reality, for example, robots that can listen to farmers. So you just give them voice commands, and robots can follow that one. This is some of the futuristic on the publications. People talk about selecting the fruits, for example, and the robot will pick that. One hot topic these days is about heterogeneous multi-robot system, which means, for example, UAV, drones, and ground-based mobile robotics, as you can see in that pictures. And also fully autonomous AI-driven. This is something that we should expect to see in the next 10 to 20 years. And one of the research and development project we are doing for oil palm plantation in Malaysia is this heterogeneous robot. The idea is that the mobile robots in the fields in plantations are expensive, but the drones, you can buy them for 200-300 euros, and you can use them as the eye, so the drone would fly ahead of the robot. Anyway, this video doesn't work. So we have this simulation that shows the robot moves ahead of the robot, the drone, and then the robot follows that one. So it creates a safe path in the field. And then the using of this digital twin. This really saved us a lot of time, a lot of cost, because you can see we had this very expensive mower that we designed, and we didn't want to destroy it in different parts of the fields. We had, this kind of situation, and that's why also to tune our algorithms with digital twins, so we could have an idea what should we expect in this kind of situation. You see the traction, friction between the tire and the field, or even what if we want to use another platform, another tractors. We didn't have that solution right away, so even selection of the platform was a question. And this is one of the recent projects that we are using also for digital twin. This is for potato fields in Germany. Now it's going autonomous, and then its job is to pick and place sensor boxes in the field, and this is connected to a simulated robot that can pick the boxes. You can see we are here doing, and also from simulation to real world to simulation. Here we are generating new joint control data based on the new scenarios that happens. Yeah. Okay. Let's go to the conclusion. So we talked about the 4 dimensions of digital agriculture and the sensing, connectivity, thinking, and acting. And the trends in agricultural robotics direction is about inside a heterogeneous multi-robot system, digital twins, swarm robotics, connectivity. And the success of automation and robotics in future crop production, in my opinion, depends on technology adaptation and affordability, that it must be accessible, it must be cost-effective solution for farmers. Some basic knowledge is required by farmers to have, just like the way we are using our cell phones, and we have some basic knowledge how to use computers and cell phones, same for robots. But the idea is that we make the robots as simple as possible with just one push of button. They should be able to work it, but still they need to maintain it. And most importantly, to have infrastructures. Farmers, if they cannot lose the season, so if the robot is out of order, they should be able to replace it. So shops, repair shops, warranties, supports, governmental supports. For further study about this, we have published 3 papers about this Internet of Robotic Things you can refer to. And I think that concludes my slide. If you can go to the next one. And there are 2 books we have on the use of mobile robotics for digital farming, and also 1 published papers with multi-co-authors about digitalization of agriculture for sustainable crop production that I would suggest. Thank you very much for your attention.